Good day everyone. Myself Vaidehi, working as Assistant Professor in Sri Muthukumaran Institute of Technology. Today the video lecture is from the subject EC3452 Electromagnetic Fields and the topics from the Unit 2 of Electrostatics. The topics are Electrostatics Fundamentals and Applications. Before going to the topic, let's see what is electrostatics and their fundamentals. Electrostatics is an important branch of electromagnetic field theory that deals with the study of electric charges at rest and the forces that exist between them. It explains how stationary charges interact with each other and how they influence the space around them through electric fields. The concepts of electrostatics are fundamental in understanding how energy is stored in electric fields and how materials behave under electric influence. This knowledge forms the basis for various practical applications such as capacitors, insulators, sensors, microelectronic devices, and many more electronic and electrical and systems. Next, see what is electrostatics. Electrostatics is defined as the study of electric charges that are stationary in nature and the electric forces that act between them. When charges are at rest, they create an electric field in the surrounding region of space. This electric field determines how other charges placed in that region will behave. Electrostatics also deals with how energy is stored in electric fields and how different materials respond when subject to electric forces. Understanding electrostatics is essential in analyzing electrical insulation systems, semiconductor devices, and energy storage mechanisms such as capacitors. Next, we see about the electric field and Coulomb's law. According to Coulomb's law, the force between two stationary point charges is directly proportional to the product of the magnitude of the charges and inversely proportional to the square of the distance between them. This force acts along the line joining the two charges and may be either attractive or repulsive depending on the nature of the charges. The electric field is defined as the force experiencing by a unit positive charge placed at a point in space. It represents the influence that a charge exerts on its surroundings. Electric field lines originate from positive charges and terminate at negative charges, and the density of these lines indicates the strength of the electric field. Next, we see about the Gauss law, the electric flux connection. Gauss law establishes a relationship between the electric flux passing through a closed surface and the total charge enclosed within that surface. Electric flux is a measure of the number of electric field lines passing through a given surface. According to this law, the total electric flux through any closed surface is directly proportional to the net charge enclosed within that surface. Gauss law is extremely useful in solving electric field problems involving symmetrical charge distributions because it simplifies complex calculations into manageable mathematical expressions. Next, we see about the applications of Gauss law. Gauss law can be applied to determine the electric field intensity for different symmetrical charge distributions such as infinite line charges, infinite plane sheets, and spherical shells. For an infinite line charge, the electric field decreases with increasing radial distance from the line. In the case of an infinite plane of charge, the electric field remains uniform and independent of the distance from the sheet. For a uniformly charged spherical shell, the electric field outside the shell behaves as if the entire charge were concentrated at the center, while inside the shell, the electric field becomes zero at every point. Next we see about the electric potential and the potential energy. Electric potential at a point is defined as the work done in bringing a unit positive charge from infinity to that point against the electric field. It represents the potential energy stored per unit charge. The electric potential is related to the electric field by a negative gradient relationship, indicating that the electric field points in the direction of decreasing potential. For a point charge, the equipotential surfaces from concentric spheres around the charge and are always perpendicular to the electric field lines. These concepts are essential in understanding energy storage in electric fields. Next we see about the conductors in static electric field. In electrostatic equilibrium, the electric field inside a conductor is always zero. This is because free electrons within the conductor rearrange themselves in such a way that they cancel any internal electric field. As a result, all excess charge resides on the outer surface of the conductor. Conductors also have the ability to shield their interior from external fields. This phenomenon is known as electrostatic shielding. This principle is used in devices such as Faraday cages to protect sensitive electronic equipment from external electric disturbances. Next we see about the dielectrics in static electric field. Dielectrics are insulating materials that do not allow free movement of charges but become polarized when subject to an electric field. When an electric field is applied to the molecular dipoles within the dielectric material, align themselves in a particular direction, produce an opposite electric field. This reduces the net electric field strength within the material. Dielectrics are characterized by a property known as dielectric constant, which determines how effectively the materials can store electric energy. They play an important role in capacitor design by increasing the capacitance. Finally, we see the summary. In summary, the electrostatic deals with the interaction of stationary charges and the electric fields they produce. Coulomb's law explains the force between charges, while Gauss' law provides a convenient method for calculating electric fields for symmetrical charge distributions. Electric potential connects field concepts with the energy considerations. The behavior of electric charges in different materials such as conductors and dielectrics determine the performance of various electrical and electronic devices. Such electrostatics forms the foundation for many modern technological applications. Hope you all understood. Thank you.